Good evening. My name is Eric Westerberg, and today I'm going to be talking about a little bit about permutation groups. The big main question for us to focus on is what are permutation groups? And we're going to delve in even to more subtopics of where does the permutation groups come from, what properties do permutation groups have, and what are they composed of? To answer that first sub-question, we have to focus on the symmetric group. Well, the symmetric group, it consists of n possible permutations. We have worked a little bit with the symmetric group S3, which has a collection of 3 factorial permutations, which is just 6 permutations. And this can go on all the way up to n possible permutations that a symmetric group could have. Later, we're going to be focusing on the symmetric groups of S1, S2, and S3 to kind of get a bigger picture of where permutation groups come from. But first, we just need to establish ourselves with the symmetric group and the fact that permutation groups come from the symmetric group. More specifically, permutation groups are a set of permutations, which is the collection of any permutation that forms a group under the composition of functions. And here in the future, when we get to the future slides, the composition of functions is pretty simple, and we've talked about that in previous work with our textbook so far. The composition of functions is all you have to do is compose the permutation on the right with the permutation on the left, and then from there, you're going to have your final permutation. And we're going to delve a little bit more into more simple examples as we go further. But to break the definition of permutation group down even further, we're going to split it up into 2 different words: permutations and groups. So if we can focus on a little bit of what permutations are and how a collection of permutations can become a group, we'll have a better understanding of what permutation groups are. So first, we'll focus on what permutations are. Well, it's a set S that is a one-to-one mapping of S onto itself, S. So let's focus on the set 1, 2, 3, 4, and 5. Well, the mapping is going to be onto the set 1, 2, 3, 4, and 5. And so if we want to use some basic permutations with the same set, how about we focus on the permutation P1, which is the disjoint cycle 2, 3, and 4, and the permutation P2, 1, 5, and 3. These are called disjoint cycles because, as you can see in P1, 2, 3, and 4 don't share any elements of anything else in the set 1, 2, 3, 4, and 5. And what I mean by that is there are fixed elements, 1 maps to 1 and 5 maps to 5, which makes the cycle 2, 3, and 4 disjoint. The same goes for 1, 5, and 3. 2 maps to 2 and 4 maps to 4. So with these permutations, we're going to practice the composition of functions using it with permutations now. So as you can see, if we take P2 and compose it within P1, using the tables that I just referred to in the previous slide, we'll first start with P2. Well, P2, 1 maps to 5, and then from there, we go up to P1 and 5 maps to 5. So when P2 is composed within P1, 1 will map to 5. And we continue this process for this collection of compositions of P2 within P1, and you're going to end up with the cycle 1 maps to 5, 5 maps to 4, 4 maps to 2, and 2 back to 3. And now you can see when P1 is composed with P2, we're going to get a different cycle. We'll go through the exact same process, but a different cycle, and it turns out that the composition of permutations is in fact not abelian. Moving forward, we've worked with permutations now. We have background knowledge of what permutations are. And now to figure out what permutation groups are, we're going to be working with permutations and see how they kind of form this group. Well, we're very comfortable with what the properties of groups are. We've done a lot with this. You need to be closed under a certain operation, and you need to be associative, you need to have an identity, and you need to have the existence of inverses. And for this particular presentation, we're going to focus on what we're comfortable with, which is the symmetric group S3. Now, we're going to even focus even more specifically at S3 at subsets of S3. These subsets that we're going to be working with are the collection we're going to call what our first subset, A3, which is the collection of permutation 1, 1, 2, and 3, and 1, 3, and 2. And then the other subset of S3, which is 1, 1, 2, and 1, 3. Now, we're going to show that one of these is in fact a subgroup of S3, and the other one is in fact not a subgroup of S3, and just a subset. We're going to start with W3. Now, Right off the bat, we're going to check if it's closed, which is the first property of it being a group. And as you can see, when you permute the orange and then with the yellow, you're going to have elements that weren't in the original set W3, which makes W3 not closed. Therefore, right off the bat, we know that W3 is not a subgroup because it's not a group, but it is still a subset because it has a collection of permutations from the original group, S3. Moving forward to now checking if A3 is a subgroup, we're going to first start with closed. Well, as you can see, when orange is permuted with yellow, you're going to have elements that were in the original set A3. Therefore, it is closed. To check associativity, we need to know that the composition of functions is in fact associative. And we've done proofs with it like this before and have shown that function composition is in fact associative. However, I'm going to show you an example of this firsthand. We have the Cayley table of what A3 looks like in the left-hand corner to kind of focus our attention. Well, we're going to be focusing on, for this particular example, the permutation 1, 3, and 2. We're going to compose it with each of the elements in A3 to see if function composition in this example is actually associative. Now, when we have associativity, we need to check if P composed with Q and then composed with R is equivalent to Q composed with R, then with P. Well, as you can focus on with the colors, if you do the yellow first, the P and the Q, and then compose it with R, you're going to end up with the identity permutation, 1 maps to 1, 2 maps to 2, and 3 maps to 3. And if you do the same thing the other way, you're going to end up with the identity permutation again, which in fact shows that this collection of elements in this particular example is associative. We can do this for all the other examples in this particular subset, and we would also show that it's associative because function composition is associative. Perfect. 2 more. Is there an identity existing in A3? Well, certainly. When the permutation 1 is permuted with 1, you get the identity permutation 1. And when you do 1, 2, and 3 with 1, 3, and 2, you get the identity permutation, and then 1, 3, and 2 with 1, 2, and 3. And obviously, there's going to be, in that particular case, that's the existence of inverses. Well, we just did that, and now the identity does in fact exist because when you permute anything with the identity permutation 1, you're going to get back to itself. And since we already just mentioned inverses, we can move along through that. We've checked out all the properties of that being a group, and in fact, A3 is a group and a subgroup of the symmetric group S3. And this is actually a special subgroup of S3, and it's called the alternating group. The alternating group of S3 just certainly means that it is the largest subgroup of S3 without being S3. So we've been talking a lot about what S3 is, the symmetric group, and what some subsets of S3 are and how they behave. Well, let's kind of delve a little bit further now into where these permutation groups come from, which are in fact the symmetric group. So, let's start with the most basic symmetric group, S1. We'll have 1 factorial elements. So that means we just have 1 element. And in order for it to be a group, you need to have the identity permutation. So that's literally the only thing that exists in S1. 1 maps to 1. For S2, you're going to have 2 factorial elements, which is just 2 elements. You need the identity for it to be a group, therefore 1 maps to 1 and 2 maps to 2. But you're also going to need 1 mapping to 2 and 2 mapping to 1. And this exchanging of elements is called a transposition. So these 2 different permutations are the only 2 permutations that are in S2. Therefore, S2 is only collected of permutation 1 and 1 mapping to 2. Now, focusing on S3, we just said earlier it's going to need 6 elements because it's 3 factorial is going to be the order. Right off the bat, we know the identity is going to exist. 1 maps to 1, 2 maps to 2, and 3 maps to 3. Well, we also know our transposition properties are going to exist as well. The exchanging of 2 different elements. 1 mapping to 2, 2 mapping to 1. And when you have a transposition with 3 elements, that means you just fix the third. So for the second one, 1 maps to 3, 3 maps to 1, fix 2. 2 maps to 3, 3 maps to 2, fix 1. That's only 4 possible permutations. We need 2 more. Well, We've already been working a lot with A3 so far, so it's going to be our permutation 1, 3, and 2, and 1, 2, and 3. Those need to be the remaining elements, and with those exchanges, we now have our 6 possible permutations in S3. And something that you can now notice is that S1, which is the identity permutation, the permutation 1, is a subset and a subgroup of S3. S2 also belongs in S3. It's the permutation 1 and the permutation 1, 2. So as you go further and further along, this property is going to exist. Now, you just delve a little bit into S3. Well, there's a Cayley table for us to kind of look at, to kind of organize our thoughts. As you can see, the identity does exist. Anything permuted with 1 is going to get back to itself. The existence of inverses is there because anytime you permute one element with another, particular another element, you're going to end up with the identity permutation. It's closed, and we can check that it's also associative. Therefore, we're just showing right now that S3, by the site of the Cayley table, is in fact a group. Now, to kind of conclude, all permutation groups come from S3. I just kind of gave you 2 examples of how S2 and S1 actually come from S3, and they are in fact permutation groups. And permutation groups are just simply a root of the symmetric group, and our branches, well, the symmetric group is the root, and the branches off from that tree are the permutation groups. So, to conclude, we now know a little bit more about what permutation groups are, and that they come from the symmetric group. And we've answered all main question and our sub-questions for this presentation. Thank you.